Welcome to this exploration of what may be the most important engineering paper ever written. In 1948, Claude Shannon, a 32-year-old mathematician at Bell Labs, published A Mathematical Theory of Communication in the Bell System Technical Journal. In doing so, he single-handedly invented the field of information theory, the mathematical foundation for all digital communication. Every text message you send, every video you stream, every file you download exists because of the concepts Shannon introduced in this paper. Let's understand how one person created the science of the digital age. Before Shannon, communication engineering was a craft without a science. Engineers designed telephone systems, telegraph networks, and radio transmitters using intuition, experience, and trial and error. There was no way to answer fundamental questions. What is the maximum rate at which information can be transmitted? How do you measure the amount of information in a message? Can you communicate reliably through a noisy channel? Engineers knew noise-corrupted signals, but they didn't know if perfect communication through noise was even theoretically possible. Shannon changed everything by asking a simple question: what exactly is information? Claude Elwood Shannon was born in Michigan in 1916. He showed an early talent for building things. As a child, he constructed a telegraph system to communicate with a friend half a mile away. At MIT, Shannon wrote a master's thesis applying Boolean algebra to electrical circuits, work that would later prove essential for digital computer design. During World War II, he worked on cryptography at Bell Labs, where he developed many of the ideas that would appear in his 1948 paper. His classified work on secure communication directly informed his understanding of information and redundancy. Shannon's first revolutionary insight was defining a unit of information: the binary digit, or bit. A bit is the amount of information needed to distinguish between two equally likely possibilities. When you flip a fair coin, the outcome conveys exactly one bit of information. This seems obvious now, but it was radical. Shannon showed that information could be quantified, measured like length or weight. Why binary? Shannon proved that any information can be encoded in binary form, and that binary encoding is optimal for many purposes. This insight underlies all digital technology. Shannon defined the information content of a message source using a concept he called entropy, borrowing the term from thermodynamics. For a source that produces symbols with various probabilities, Shannon's entropy formula is H R S E A X log 2p, where p is the probability of symbol I. What does this mean? High entropy means high uncertainty, more information per symbol. Low entropy means predictability, less information per symbol. Example: if a weather station reports sunny 99% of the time, a sunny report conveys little information. A rainy report would be surprising and informative. Shannon's entropy captures this intuition mathematically. Shannon's first major theorem addresses data compression. What is the minimum number of bits needed to encode messages from a source? The source coding theorem states you can compress a message source to approximately h bits per symbol, but no further without losing information. This gives a fundamental limit. If your source has entropy of 3 bits per symbol, you cannot compress it to 2 bits per symbol without losing information. But you can get arbitrarily close to 3 bits. The implication: Shannon proved that efficient compression is possible and quantified exactly how efficient it could be. This is why we can compress text files, images, and videos. Shannon showed where the fundamental limits lie. Shannon analyzed English text and found it has significant redundancy. He estimated the entropy of English at about 1 to 1.5 bits per character, far less than the 4.7 bits you'd expect from 27 equally likely symbols. This redundancy is why you can understand a sentence with missing letters. Predictive text works on your phone. English text can be compressed significantly. Shannon's analysis of language redundancy also had applications to cryptography. The more redundant a language, the more vulnerable to cryptanalysis. Shannon introduced a model of communication that remains fundamental today: information source, transmitter, channel, receiver, destination, with noise affecting the channel. The source produces messages. The transmitter encodes them for transmission. The channel carries the signal but adds noise. The receiver decodes the signal. The destination receives the message. This simple model unified all forms of communication. The most profound concept Shannon introduced was channel capacity, the maximum rate at which information can be reliably transmitted through a noisy channel. For a channel with bandwidth W and signal-to-noise ratio Sn, Shannon derived the famous formula C airs or WX, log 2 bits per second. This is the Shannon-Hartley theorem. It says that a channel's capacity depends on its bandwidth and signal-to-noise ratio, but nothing else. The revolutionary implication: before Shannon, engineers tried to fight noise by increasing signal power without bound. Shannon showed there's a fundamental limit. You can't exceed capacity no matter how much power you use. Shannon's most surprising result was his noisy channel coding theorem. If your transmission rate is below channel capacity, you can achieve arbitrarily low error probability through proper encoding. This was astonishing. Engineers had assumed that noise inevitably caused some errors. Shannon proved that with the right coding scheme, you could communicate perfectly reliably through a noisy channel, as long as you stayed below capacity. The converse is also true. Above capacity, reliable communication is impossible. There's a catch. Shannon proved that good codes exist using probabilistic arguments. He showed that a random code would work with high probability. But he didn't construct specific codes. His paper was an existence proof. Reliable communication is possible, but finding practical codes was left as an exercise for future engineers. This launched decades of research into coding theory: Hamming codes, Reed-Solomon codes, convolutional codes, LDPC codes, turbo codes, polar codes. By the 2000s, practical codes approached Shannon's theoretical limits within fractions of a decibel. Shannon's theory underlies all digital communication, from your cell phone calls to the vast network of the internet. Your voice is digitized, compressed, and protected with channel codes transmitted at rates approaching Shannon's capacity limit. The internet's TCP/IP includes error detection, while Wi-Fi and Ethernet use sophisticated channel codes to maximize throughput. Deep space probes communicate across billions of miles using powerful error-correcting codes, a testament to Shannon's enduring impact. Storage media like CDs, DVDs, hard drives, and flash memory all rely on error-correcting codes derived from Shannon's theory. Shannon's source coding theorem is the foundation of data compression, enabling both lossless and lossy methods. Lossless compression, like zip files and PNG images, approaches Shannon's entropy limit, compressing data without any loss of information. Lossy compression, used in JPEG images and MP3 audio, removes information humans don't notice, achieving even greater compression. Modern codecs like H.265, video compression, and Opus Audio represent decades of approaching Shannon's theoretical limits. Shannon's paper enabled the digital telephone networks, compact discs, and early internet protocols of the 1970s and 80s. The 1990s brought the World Wide Web, digital cellular networks, and MP3 audio, all built on his foundational work. The 2000s saw streaming video, smartphones, and social media emerge, fundamentally shaped by Shannon's insights. From 2010 to the present, cloud computing, 5G networks, and machine learning systems processing vast amounts of data continue to rely on his theories. Shannon's genius extended beyond this one paper, influencing Boolean algebra for circuits, essential for digital computer design. His classified work during WPUIS and his 1949 paper on secrecy systems founded modern cryptography. Shannon also wrote early papers on chess programming and machine learning, pioneering artificial intelligence. He approached profound problems with playfulness, building a flame-throwing trumpet and a rocket-powered frisbee. Shannon's paper established concepts that pervade modern science, such as mutual information, which appears in machine learning and neuroscience. His rate distortion theory, a later work, founded the essential theory for lossy compression, asking how much data can be compressed with some loss. Shannon's work inspired the idea that information is as fundamental as matter and energy, influencing quantum computing and black hole physics. His approach offers lessons for modern researchers. Fundamental questions matter, and abstraction is powerful. By ignoring physical details, Shannon created a theory applicable to all communication systems, proving that existence proofs are valuable. His paper uses relatively simple mathematics to reach profound conclusions, demonstrating that simplicity and depth can coexist. Every time you send a text message, stream a video, or make a phone call, you're using technology built on Claude Shannon's 1948 paper. Shannon gave us the mathematical language to understand communication itself, showing that information is precise and measurable. In a world drowning in data, Claude Shannon taught us what data actually is. His paper is the operating manual for the information age.